We will continue EPA 608 Universal Certificate, this type 1, and we are now here in part of recovery. We'll start with the refrigerant recovery. Refrigerant properties.
In this module, we will take a look at how to read pressure-temperature charts. We will also discuss the pressure-temperature relationship of refrigerants and talk about how to use it to see whether there are non-condensables present.
Each substance has a unique saturation pressure-temperature relationship. By this, we mean that for every known refrigerant, there is a specific saturation pressure given a specific temperature, and vice versa. If we list out all the saturation pressures of R22 or HCFC22 at different temperatures, we get a PT chart that looks like this. A PT chart is a saturation pressure temperature chart. To read this chart, let's zoom in. The units for temperature are either degree Fahrenheit or degree Celsius, as we can see up here. The units for saturation pressure is given in the middle where it says pressure. In this case, the pressure will be given in units of psig. To find the pressure of refrigerant at a specific temperature, we look for the temperature, then look across the row for the corresponding pressure. For example, at 10 degrees Fahrenheit, we see that the saturation pressure at the temperature is 32.8 psig. At 50 degrees Fahrenheit, the saturation pressure of R22 is 84.1 psig. This means that if it is at 50 degrees Fahrenheit, the pressure will be 84.1 psig, assuming the refrigerant is in a saturated state. At this pressure, R22 can exist as both a liquid and a vapor. The inverse is also true. If the pressure is 84.1 psig, the temperature must be 50 degrees Fahrenheit. This works both ways as long as the refrigerant is in a saturated state. Remember that this chart is specific to the refrigerant R22. If we wanted to do this for another refrigerant, we would have to look up the PT chart for that refrigerant. For example, for the refrigerant R134A, we would look up our R134A PT chart.
What is the approximate pressure of a storage container of R22 that is stored at 75 Fahrenheit? Assume there are no impurities. Use R22 chart like this. Okay, we will use the chart. It is asking that R22, okay, at 75. He's asking for pressure. Okay, this R22 pressure chart, we will go to temperature 75. Okay, temperature here 75. We will find here the pressure is 132.2. 132.2. Okay. Like 131. Yeah.
For the EPA exam, we need to know how to reference PT charts too. Find a saturation pressure given a temperature, or find a temperature given a saturation pressure. For refrigerant blends, we will see two pressures in their PT charts: vapor pressure and liquid pressure. This is because the different components of the blend may be in different states at a given temperature. This is the PT chart for R404A, which is a near azeotropic blend. Earlier, we talked about how near azeotropic refrigerant blends act almost like azeotropic blends. As a result, the components of the blend have a small difference between their boiling points. We see this reflected in the small difference between liquid and vapor pressure in our 404A's PT chart. We learned that zeotropic refrigerant blends contain components that have different boiling points. For refrigerant blends that are zeotropic, we will see a larger difference between the two pressures. For example, we see a much larger difference in the pressures with our 407C, which is zeotropic. We also discussed how zeotropic blends contain components that have the same boiling point. For zeotropic or near-azeotropic blends, the difference between the liquid pressure and vapor pressure is much smaller, if there is one at all. For example, we see a much smaller difference in pressures in the near-azeotropic refrigerant R404A.
Near azeotropic blend will contain one saturation pressure value, one high saturation pressure value to saturation pressure value that are close, two saturation pressure values that have big difference. I think this is difference. No, they are close. Oh, yeah. For blend, near azeotropic blend contain multiple components that have close saturation pressure, if not the same pressure value. Azeotropic blend will contain one saturation pressure value. We said two saturation pressure values that are close. Azeotropic, not close. Zeotropic blends have large difference between their saturation pressure. What is the approximate pressure of a storage container of R404 that's stored at 60? Assume that 60 Fahrenheit. Assume that they are no impurities. Sorry. Now this R22. Okay. But we need we need the chart. Okay, let's open the chart. Now PT chart. Okay, PT chart, we have here R404A. Assume there are no impurities for stored in 60 Fahrenheit. This needs the maximum pressure. 404A, 409, 4014. Okay, we need this 404 in 60 Fahrenheit. We'll go here 60 Fahrenheit. We'll find here 123. This is the nearest one. 125. Yeah.
The pressure-temperature relationship is kind of like the fingerprint of a refrigerant. We can look at a refrigerant's PT chart to see what the pressure of a refrigerant has to be at a specific temperature. We can use this pressure-temperature relationship to see if there are non-condensables mixed in with the refrigerant. To use this relationship, we need to measure both the pressure and temperature of the refrigerant. If we measure the temperature and pressure values of a refrigerant and they are not similar to the PT chart values, it means there are non-condensables present in the cylinder. Non-condensables in the refrigerant affect the refrigerant pressure at different temperatures.
We can use a known refrigerant PT chart to see if there are non-condensable in the refrigerant. We can use known refrigerant PT chart to see if there are non-condensables in the refrigerant. Always true, only true if we can measure the refrigerant temperature. Only true if we can measure the refrigerant pressure. only true if we can measure both pressure and temperature. Yeah.
For example, let's say we know that the refrigerant is R22 and the temperature is 70 degrees Fahrenheit. In that case, the pressure of the refrigerant should be 121.4 pounds per inch 2 gauge. If we measure the pressure to be 130 pounds per inch 2 gauge, then that means there are non-condensables present because the pressure does not match. If the pressure is 122 or 120 pounds per inch 2 gauge, this is close enough to mean the reading's accurate, and the difference may be due to human error. In order to use pressure and temperature readings to check for non-condensables, we need stable pressure and temperature readings. For example, if the temperature of the room changes from 70 degrees Fahrenheit to 75 degrees Fahrenheit during the test, we cannot use those temperature values to compare against the refrigerant's PT chart.
If a refrigerant pressure reading are not stable, we can use its temperature reading to compare to its PT chart to check for non-condensable. No.
Let's say we recover R22 from a system into a recovery cylinder and want to check if there are any non-condensables inside the recovery cylinder. We need to first make sure that the pressure and temperature are stable, so we must let the recovery cylinder rest until its temperature matches the room temperature. This lets us know that the temperature won't change in between readings. After the recovery cylinder achieves room temperature, you can then perform the following steps to verify its pressure. Look at the system's high side pressure, then use your PT chart to check what the pressure should be. If the values are close, it means that you do not have non-condensables in your refrigerant. If they're not close, it means there are non-condensables present and you need to recover, evacuate, and recharge the system. We evacuate the system to get rid of the non-condensables.
Which of the following values do we check if we suspect that non-condensate are present? Which of the following values do we check if we suspect that non-condensable are present? Refrigerant pressure, humidity, refrigerant type, refrigerant weight, refrigerant pressure. Yeah. If the pressure reading and the expected pressure are far apart, which of the following are possibly contained in the refrigerant? Non-condensable, water vapor, nitrogen, water vapor. Oh no, non-condensable. The pressure reading is not close to the expected pressure. It is indicates that the presence of non-condensable in the refrigerant. Remember that water vapor and nitrogen are examples of non-condensable. So this means all of above.
In this module, we learned how to make sense of and use PT charts. We also learned how to use these charts to see if there are non-condensables in a cylinder of recovered refrigerant.
Okay, we finish this part. Let's continue. Okay, refrigerant properties. Let's go to recovery requirements.
In this module, we will take a look at the two main methods of recovering refrigerants and discuss the different requirements for each method.
System-dependent recovery requires the pressure of a functioning compressor to recover refrigerant. It is also called passive recovery. We learned that in any system, matter will flow from a region of high pressure to a region of low pressure. Since the refrigeration system is pressurized by the compressor, we can use that pressure as our high point. If we connect a non-pressurized refrigerant container to the system, the pressure of the container is lower than the pressure inside the system. The refrigerant will naturally flow from the system, high pressure, to the cylinder, low pressure, helping us recover the refrigerant. This is how system-dependent recovery works. Passive recovery is limited to appliances with 15 pounds or less of refrigerant. This includes small appliances with less than 5 pounds of refrigerant, like household refrigerators. These are the appliances which we cover in Type 1.
System-dependent recovery is the same as passive recovery, uses pressure of the compressor, can be used for appliances that's under 15 pounds of refrigerant, yeah, all of above. System-dependent recovery, capture refrigerant in pressurized container to keep it fresh. False. With system-dependent recovery, we use a non-pressurized container to capture the refrigerant.
Self-contained recovery involves the use of a recovery device that operates independently of the system you are recovering refrigerant from. They have their own compressor, pump, or other mechanism to help recover refrigerant from the system. This is also called active recovery. When recovering from small appliances, you must first identify the refrigerant that you are about to recover. Older refrigerators, particularly those built before 1950, may contain non-fluorocarbon refrigerants, which cannot be recovered with modern recovery equipment. Active recovery does the job much quicker than passive recovery. Remember, as the time for recovery increases, the chances of venting refrigerant also increase. As a result, we want to minimize the time spent recovering refrigerants as much as possible. Active recovery is required for systems containing more than 15 pounds of refrigerant.
An active recovery machine is required for all systems. Passive recovery is a thing of the past. No.
There are different recovery levels depending on whether the appliance's compressor is working. When the compressor in a Type 1 appliance is not working, EPA Section 608 regulations mandate recovering at least 80% of the charge amount indicated on the appliance's nameplate. For appliances with working compressors, EPA Section 608 rules require either recovery of 90% of the nameplate charge or recovery of the appliance to 4 inches mercury. For example, if you come across an appliance with a non-functional compressor and a charge of 5 pounds indicated on its nameplate, you would need to recover 80% of the refrigerant charge, or 4 pounds of refrigerant. If the same appliance has a working compressor, we would need to recover at least 4.5 pounds of refrigerant.
For both active recovery and passive recovery, we must recover 80% of the appliance's charge if the compressor is not working. Yeah. When performing active recovery and the compressor is working, we must recover to what level? 90% of the refrigerant charge, 4-inch vacuum, both of the above, either 90. Yeah, I think both. No? Either? Yeah.
With an operating compressor, there should be a big enough pressure difference between the system and your recovery container. The pressure difference makes the refrigerant naturally flow from high to low pressure, so it flows from the system into the recovery container. In a system with an operating compressor, you only need to have one access valve to recover refrigerant. Such a system requires a completely restricted capillary tube, on one side of which we attach the access valve. This must be done on the high side of the system.
Let's say we have a system with an operating compressor and the capillary tube is completely restricted. How many access valves do we need to recover refrigerant from systems that it is sealed? Okay, two, I don't know. One, correct. We only need one access valve to recover refrigerant from sealed system with an operational compressor.
One of the reasons a compressor fails to work is that there is refrigerant trapped in the compressor oil. Technicians need to take measures to help release this trapped refrigerant. This is especially important in passive recovery, since the recovery process relies on the system's pressure. It is essential to take appropriate measures to release trapped refrigerant when performing passive recovery on a system with a non-functional compressor. Since refrigerant is miscible in refrigerant oil, it can get trapped in the oil. It is separated when we heat up the mixture and the refrigerant vaporizes and leaves behind the oil. This is how we release trapped refrigerant.
If the compressor is not working and we are performing passive recovery, we need to take steps to do that. Secure recovery machine, vacate the area, ventilate the working space, release trapped refrigerant from the compressor oil. We need to release trapped refrigerant.
These measures for releasing trapped refrigerant include warming the system with a heating blanket or heat gun and tapping the compressor bottom with rubber mallet to release refrigerant. Make sure to warm up the cylinder with a heating blanket, not an open flame. We learned from the core module that open flames can cause an explosion since refrigerant cylinders are pressurized, and some refrigerants may be highly flammable. When tapping the compressor to release trapped refrigerant, it is important to use a rubber mallet. We need to make sure not to damage the appliance. Using a metal mallet is risky because it may damage the appliance, causing the release of refrigerant, or damage the equipment irreparably.
What should we do to recover refrigerant from a system with a compressor that it is not working? Okay. What should we do to recover refrigerant from a system with compressor that's not working? Okay. Trapping the compressor with the biggest mallet to maximize the service area. Tapping the compressor with a rubber mallet so we don't damage it. Heating it with a match. Heating it with a heating blanket. Yeah.
When performing passive recovery on a system with a non-functional compressor, we need to access the system from both the high and low side to recover as much refrigerant as possible. Remember that during passive recovery, the recovery process depends on the compressor. With a non-operating compressor, accessing both high and low sides allows us to get to the 80% recovery level.
When the compressor is not working and we are performing a passive recovery, we need to access the system from both the high and low side. Okay, yeah, correct. When it's come to passive recovery, the process depends on the pressure of the compressor. If it's not working, we need to access both the high and low sides of the system to recover as much refrigerant as possible.
Technicians need to take measures like this to make sure that they recover the required refrigerant level of 80% of the nameplate charge when the compressor isn't working. In this module, we discuss the requirements for recovering refrigerants in Type 1 appliances. For appliances with non-functional compressors, we need to recover 80% of the nameplate charge. This is required for both passive and active recovery. For active recovery on appliances with working compressors, we need to recover either 90% of the refrigerant charge indicated on the nameplate or up to a 4-inch vacuum.
Okay, now we will go to the next step, this recovery procedure. Okay,
In this module, we will take a look at how to recover refrigerant and waste to speed up the refrigerant recovery process.
let's start.
Over is recovery and the hose setup. All right. So in this case, we're looking to recover 134A refrigerant, and so we have our 134A gauge set, and we have our hoses, and we have our 134A recovery bottle. So you're going to keep each recovery bottle labeled so you know what refrigerant's inside of it. So the supply houses will normally take HFCs for free and exchange them with an empty bottle. You just need to buy their bottle from them originally. So we buy a 50-pound recovery bottle, and it's really not that much money. You buy that, and then you can recover your refrigerant, make sure it's only one refrigerant, and then when you have that completely full, then you can go ahead and exchange that for free. All right, it doesn't have to be completely full, but they will exchange it. All right, if it's R22 refrigerant or R12 refrigerant, they will buy that refrigerant off of you. Now you have to check with your local supply house to see if they're purchasing refrigerants or not, and if so, then you're going to likely need their bottle. They also sell likely disposable bottles as well that you can just do a one-time fill with. All right, so R22 right now, presently, as of this date, which is September 2016, R22 at the supply houses where I'm located at, they're paying $3.50 a pound. Okay, so anyway, first things first, the recovery bottle. We turn our scale on, it reads 0, and then we're going to need to weigh it to check our initial weight in the tank. All right, so we're reading 36 pounds and 12 ounces. All right, on the side of the tank, it's either going to be right here or right back here. You're going to find a tare weight, and a lot of times they're right around 26 to 28 pounds. So you have to find the tare weight. This one actually says 27.9 lb, so that means about 28 pounds. All right, so you can fill a recovery tank 80% of the way. You can't put 50 pounds of refrigerant in a 50-pound recovery cylinder. You can only put 80% of that in there. And to be safe, you can go 2 pounds shy of 80%. So in the case of a 50-pound cylinder, you can put potentially up to 40 pounds in it, but a lot of manufacturers are recommending you putting 2 pounds less than 80%. At least I know DuPont does. I don't know about other ones. So to stay safe, a 50-pound cylinder can be filled up to 38 pounds usually. All right, 38 pounds of refrigerant. 38 pounds plus the tare weight of 28, and you're looking at 66 pounds total. All right, so we know if we were at 36 pounds, that we can put another 30 pounds in this. So you have 66 minus 36, and we can put 30 more pounds of refrigerant in this. There's only 8 pounds in there roughly right now. All right, so we're good with that. Now, if we're going to recover in vapor form, we can then go ahead and put it into the vapor. If we're going to recover in liquid, we can put it into the liquid. I will tell you that regardless of whether you're recovering in liquid or vapor, if you put it into the vapor port, usually you're okay. All right, if you try to recover in vapor, make sure that you're not putting it in the liquid port, because what happens is the liquid port has a dip tube that goes all the way down to the bottom, and basically what you're doing is you're putting vapor down there, and it's bubbling up through the liquid, and it causes the tank to get really hot. So make sure that you absolutely don't do that. If you're recovering in liquid, put it in the liquid side. If you're recovering in vapor, put it in the vapor side. Worst case scenario, though, I have seen, you can go ahead and recover either way into the vapor side. Because you're just putting it right into the tank, all right? But the whole point is you're trying to keep the tank cool while recovering refrigerant. You don't want it to get overpressurized. So that's that. You can use these core removal tools when you're hooking into your service ports. So if you hook this right in, all right, and then you can actually pull your Schrader valve out, all right, your core valve out, and then you can close it off, and then as you're recovering, you have no restriction in the line. All right, so you can use this in order to recover a little bit faster. So since this is 134A refrigerant that we're dealing with here, when we recover the refrigerant out of the system, we're going to end up recovering it down to 10-inch HG. All right, so that's down into the green. All right, and we need to be able to hold that. So basically, while the recovery system's running and it's putting refrigerant into the bottle, what we can do is we can just close this handle down temporarily just for half a second and just check to see where this needle rises up to. If it rises up past 10-inch HG, we're just going to open it and continue to let it suck down to 10-inch HG. I'll tell you that I was dealing with out recovering 13 pounds between 0 and 10-inch HG. I had a pound and a quarter or so, right around there, between 0 and 10-inch HG of refrigerant. I would not advise, say pulling down to that level if you have a leak, because then you're just going to pull air right into the recovery tank. You don't want to do that. All right, but for HFCs like 134A and R410A, you pull them down to 10-inch HG, and for R22, if the system's below 200 pounds, then you're going to pull that down to 0. All right, but you can check out your guidelines on that at the EPA.gov just to verify those things. All right, but anyway, that's what you're doing. You're sucking the refrigerant down. So if it's 70 degrees and the system's off, and you're working with 134A, you're going to have right around 72 psig, and it'll take a little bit to recover it down to that level. But that's how you do it. All right, so you can use these core removal tools so that it doesn't take as long and your Schrader valve's not in the way. You don't have to use these. You can just go ahead and connect in and just recover right through your Schrader valve. That's fine too. All right. Another thing is if you were planning on reusing this refrigerant in the bottle and you want to keep your recovery unit clean, you can actually go ahead and put a filter dryer in place right here. Put your filter dryer in place. And if this is just a flare section right here, you're going to want to put a little bit of refrigerant oil in there beforehand, the refrigerant oil that you're dealing with. All right, and then you can go ahead, or you can put a rubber grommet in there, and then you can just connect it. Make sure that your filter dryer is saying that it is heading in that direction, which this does say. All right, see that? It's heading in that direction, in that way. All right? So that'll help keep the recovery unit clean and the tank clean. All right, so as you're recovering, the first thing you're going to do is you're going to attach these gauges in, whatever one you're going to be working with. If you're going to be working with the vapor side, you connect this right into the vapor. You can go ahead and open that up. All right, your refrigerant's going to flow through here. Then it's going to flow into the yellow hose. It's going to come all the way through. It's going to come into your recovery unit. Then it's going to flow out of your recovery unit and right over to the bottle. So this recovery unit does not have to be on. When you purge the air out of the lines, you're going to purge the air out right here. This valve, this blue valve, is still going to be closed, and you're going to purge the air out here, all right, until it's refrigerant, and then you stop, and then you close that down, all right? So then you don't have air in your lines. Then after that is when you're going to open the bottle up right here, and then you can go ahead and turn it on. So you're going to turn this on, get the air out of the lines, then close this, then tighten this hose down, open the valve, then turn the recovery unit on. All right, when you get down to 10-inch HG, the first thing you're going to do is you're going to close this down. All right, then you're going to close this down, your handle, then you're going to turn the recovery pump off.
Before beginning the recovery process, we need to first identify the refrigerant in the appliance. Afterward, we need to use a recovery cylinder that is used for that specific type of refrigerant. For example, if we are recovering refrigerant from an appliance that contains R22, we need to use a recovery cylinder that is exclusively used for R22 refrigerant. Remember, each recovery cylinder can only be used to recover one type of refrigerant. We need to use separate recovery cylinders for different refrigerants to avoid mixing and making the refrigerants unusable.
We need to separate recovery cylinders for each class of refrigerant. Example HCFC. For example, we cannot use the same cylinder to recover CFC and HCFC refrigerant, but we can use the same cylinder to recover different HCFC refrigerant. Yeah. It's we need to separate, but we cannot use the cylinder for another issue. You are servicing an appliance that contain R134A. Which of the following can you use to recover the refrigerant? Okay. Which of the following can you use to recover the refrigerant? A recovery cylinder used for HCFC 22. No. A disposable cylinder used for R134. Recovery cylinder. Not contain when you are servicing. It must be the same one, but no. Not disposable. Not disposable. Must be recovery.
When recovering refrigerant
HCFC
into a
is this
recovery
one.
cylinder, we also need to make sure we do not fill more than 80% of the cylinder's capacity. We can monitor the fill of the recovery container by using one of the following: mechanical float devices, electronic shut-off devices, or gross cylinder weight. Mechanical float devices are also called internal float devices. They work by turning the motor of the recovery machine off when a certain fill level has been reached.
I'm going to show you today is this is a float switch. This is clear inside. Ramba sent this to me, and this shows how it works. So when the switch is down, okay, the contacts, as you can see, aren't touching. So as the water rises in your tank, the float goes up, and then the ball eventually falls, and bam, it hits a switch. So then you got contact, and your pump will be running. So and then as it comes down, as the water level comes down, the ball will eventually fall and it'll turn off. Okay, so this is a very accurate way to do it. Mercuries are a little more sensitive, so as you can see, the ball actually, the switch got to come up quite a bit before it goes on. Mercuries tend to they're real sensitive because it's a liquid, and if there's any kind of movement in the tank, you can get chatter and it'll cycle the pump on and off, on and off. So we prefer a mechanical float switch. In some states you have to use a mechanical. Mercury's illegal to use. Louisiana, Illinois. I don't think Florida's outlawed them, but that's pretty much it. So on, off. So that's how a float switch works.
Even when the motor is off, refrigerant can still flow into the cylinder, leading to a fill of more than 80%. If you then warm up the cylinder, it may blow out a relief valve or even explode. For these reasons, the industry has largely shifted away from mechanical or internal float devices, and even electronic shut-off devices. Technically, however, these methods can still be used according to the EPA.
Which methods are approved by the EPA to monitor fill level of recovery cylinder, mechanical and or internal float device, electronic shut-off device, gross cylinder width,
Using the cylinder weight is
all
the most accurate
approved.
method of monitoring fill level. This method forces technicians to be more vigilant and get the recovery done in a more timely fashion, which reduces the risk of accidental venting.
Which method of monitoring fill level is the most accurate?
Remember, it
Gross
is our
cylinder weight.
imperative to minimize refrigerant recovery time because the longer we take, the more likely it is for an accident to happen. We want to prevent accidents like venting refrigerant or equipment malfunction. There are special cases where we have to take additional measures to recover refrigerant faster. It includes instances when the compressor stops working during passive recovery. One of the methods we use to recover refrigerant faster is installing both low and high side access valves. This way, refrigerant can flow through both sides, allowing us to recover it faster.
Installing both high and low sides access valves will increase recovery time.
In
Okay.
frost-free
No, it will
refrigerators, we can
decrease.
also utilize the defrost heater component to help us speed up the recovery of refrigerant. The defrost heater is a component in frost-free refrigerators that melts ice off evaporator coils so that the coils can be exposed to air. Turning on the defrost heater will increase the temperature of the refrigerant so that we can recover it faster.
Defrost heaters can be used to increase the temperature of refrigerant, can be used to increase refrigerant recovery speed, are available in all types, are
In
available in
this
all
module,
type
we
of
took a look at
appliances.
various
Yeah.
recovery practices, including
Ah, all of
identifying the refrigerant inside an appliance, the methods to use to prevent overfilling recovery cylinders, and increasing recovery speed to minimize recovery time. Next, we'll take a look at the equipment we need to recover refrigerant.
yeah. So in the recovery for type 1, we finished refrigerant properties, refrigerant requirements, and refrigerant procedure. We will check the refrigerant equipment.
In this module, we will take a look at the pieces of equipment that are commonly used when recovering refrigerant from Type 1 appliances. We will discuss the EPA Section 608 regulations for these pieces of equipment.
There are many systems that are sealed, meaning that the system is designed in such a way that it's not possible to access the refrigerant inside. These appliances do not come with ports installed for testing, recovery, charging, or evacuation. Hermetic systems are sealed systems, so this is a characteristic of Type 1, small appliances. Examples of closed or sealed systems include window AC units and refrigerators. In order to access these systems for servicing, we need to first look for process tubes. If there are no process tubes from which we can tap the refrigerant, we can create an opening by installing an access fitting. Access fittings allow us to gain access to the refrigerant in a sealed system. Make sure you have a good reason for opening up any sealed system. Access fittings must be leak tested before use to ensure there is no venting of refrigerant.
Access fittings need to be leak tested before recovering refrigerants, are used to gain access to the closed system, are used with windows AC units. I think all of this. Yeah. We generally want to leak test access fittings after a service to make sure it doesn't have leak for the next service. This is to save us time for leak testing the access fitting the next round. Yeah, you know.
Piercing valves are used to access refrigerant from the process stub on small appliances. We can use both solder type and solderless piercing valves.
I might have to move this a little bit different. On the side like this is probably okay too. We'll go close enough where it's not going to be affected by this bent part of the tube. Alright, so we'll use this handy dandy wrench here. Now I did end up facing this out, but I was able to just gently bend this tubing over just a little bit. There's a little bit of give in it, so you're okay with that, just to make enough room for this port to go on here. And we'll painstakingly tighten these up until that is totally closed across there. There's no gap at all. And right here on the bottom, there's one more Allen screw spot. And right there, we just gotta thread this all the way in until it fully seats and stops. Let's do it this way. And that's going to make a little pinhole in the copper tubing so that we can access it. So we'll crank it all the way down. Alright, so we fully seated that, and now when we loosen this, it should, yep, it opens that valve. So now we're ready to put our gauges onto this unit. And then when you're done using this line tap, you just simply close it like we closed it just now, and then put your cap on here to make sure that you don't have any leakage ongoing. And that's pretty much it. That's how you use one of these.
Say, for example, we install and open a piercing access valve. If we find that the pressure of the appliance is 0 psig, it's likely that there has been a leak. The fact that the pressure is 0 psig indicates that there is basically no more refrigerant left in the system.
If the pressure of the system is found to be 0 psi, can we recover refrigerant from the system?
If
No.
the appliance is expected to leak refrigerant, we will generally use solder-type piercing valves. This is because they are more durable and tend to hold up better over time. Solderless piercing valves tend to develop leaks over time, so they should not remain on the system after the completion of recovery.
Solderless piercing valve tend to leak over time, are for permanent use, should not be left in the appliance after service. Should not be left. Okay, so both tend to leak over time, A and C, yeah. Okay, connected and disconnected refrigerant.
Hey guys, this is AC Service Tech, and today what we're going over is what are low-loss fittings and how are they used to prevent the refrigerant from escaping into the atmosphere and to allow the refrigerant to be a little bit more controlled when you're connecting and disconnecting your refrigerant gauge set and refrigerant hoses, and also how to avoid getting the refrigerant on your skin. Now, anytime you're working with refrigerant, you want to make sure that you're wearing safety gloves just to make sure that you don't get contact with the refrigerant oil onto your hands. But anytime that we're attaching the refrigerant gauge set, such as this right here, the other end has to get connected to the service valve. So in this service valve right here is the same one as this one, and this has a valve core in it. So In order to gain access to the refrigerant in the system, this valve core right here has to be pressed in. So this one right here is a 3-position service valve. These service valves are the most common ones used on air conditioning, and then this one is typically used on refrigeration, or a version of this. This is a 3-position stem valve, and to gain access to this, there's no valve core in here, and this top stem, what you need to do is you want to make sure that this is back seated, which means the stem is up all the way. You connect your refrigerant hose right onto the port, and then you mid-seat this, and you do that with a ratcheting service wrench, such as this right here. Just a couple clicks like that and you're good to go, and then you have refrigerant coming out of the port through your hose and into your manifold gauge set in order to read your pressure. The problem comes when you're disconnecting from either one that does not have a valve core or one that does have a valve core. You don't want all the refrigerant that's in the hose connected to your manifold gauge set to come right out the end. As well, some of the low loss fittings actually make sure that the valve core right here is reseated before it even disconnects from the end, so it just makes it more controllable. Now, oftentimes you see me working with the compact ball valve. This is a manual low loss fitting. It's actually attached, pre-attached onto the refrigerant hose end. So this is what you typically see me working with out there. If you have a lesser expensive hose setup, you can actually add a compact ball valve onto the end. So right there you can actually get this, and I have these all linked down in the description below. But this one happens to be made by Yellow Jacket. You really don't want to connect into a refrigeration or air conditioning system with just a hose that looks like this, because there's going to be a lot of refrigerant that comes out when you go ahead and disconnect. If you do have one of these hoses though, you can actually add something that looks like this. And what this is a seal right coupler, and this will be referred to as an automatic low loss fitting. Because when you disconnect from the port right here, it actually holds all the refrigerant inside the hose. Now this right here can also be added on, and this is a thumb screw valve core depressor. And there's 3 versions of this particular manual low loss fitting, and there's like a very small one, there's one without a back seat, and this one is the one with a back seat. So when you attach on, you can actually lock all the refrigerant in the hose right here, and then you can go ahead and disconnect. This one is a very controlled way of disconnecting from the service valve. Presently we're just using 350 psig of dry nitrogen in the system, and the reason that we're doing that is just so that this system isn't making a lot of noise in the background while we're connecting and disconnecting, in order to get the system pressure up that high. Now we have our valve core depressor tool with the back seat and also the thumb screw attached to the refrigerant hose, and that's attached to the gauge right here. There's no rush when attaching this on because it's not pressing in on the valve core, so that's not a problem. Now we just go ahead, and once again, there's no rush when you're turning this in either. And now we're reading right around 315 psig. Now, in the other videos I've done, I've shown you the disconnect procedure for when you disconnect the liquid line from the system. You're trapping the refrigerant in the high side hose, and then you are weighing it back into the vapor side. You just got to make sure that you've already purged the air out of the refrigerant hoses. So go ahead and check out that video. Now we just go ahead and backseat this, and then we can go ahead and disconnect this off. The next one is the compact ball valve. So we go ahead and screw this in, and this is one that you have to do fairly quickly. It should seal with the rubber as long as the grommet on the end is newer, where you've taken care of it, you've replaced it when it's worn down. But anyway, you screw it in nice and tight, and then you go ahead and you read your pressure, and you shut your manual loss ball valve right here, and then you go ahead and disconnect it. Got to make sure that this is quick as well, because it's actually reseating this valve core right here as you're disconnecting. Here you have your seal rate coupler or your seal rate 90. You can get this in straight or 90 degrees, and like I said, these are all linked in the description below. I'm going to go ahead and screw this in. You want to do this fairly quickly. And you want to make sure you screw it in enough so that you're getting the accurate pressure. Then when you unscrew this, it'll actually reseat the valve core before it actually releases from the port. The rubber is actually sealing up against the port. And like I said, just go ahead and make sure that after you've trapped the liquid refrigerant in the red hose, that you're weighing it back into the vapor side so you're not wasting the refrigerant. You don't want to accidentally steal refrigerant out of the system when you're going to disconnect the refrigerant gauge set. Another thing that you could do is you could put a manual low loss or an automatic low loss fitting on the end of a
There are two main kinds of low-loss fittings, automatic and manual. In this video, the fitting attached to the red hose is automatic, and the fitting attached to the yellow hose is manual. They both work by obstructing and preventing the flow of refrigerant from the hose, which prevents venting.
Low loss fittings are required for servicing appliances containing CFC and HCFC and HFC because of venting prohibition. True. Which of the following are types of low loss fittings? Solder type of low-loss, manual low-loss fittings, automatic low-loss fittings, hybrid low-loss fittings, solder type low-loss fittings. Oh, there is something wrong? I
Low-loss
don't know.
fittings are required for servicing
Manual,
systems containing
low-loss, and automatic.
CFCs, HCFCs, and HFCs to prevent venting these harmful refrigerant substances. We must use them to comply with the venting prohibition, which applies to all ODS and their non-exempt substitutes. For these systems, low-loss fittings are required whenever refrigerant hoses are used in your service, including when recovering refrigerant and measuring system pressure. Whenever we connect our hoses to measure the system pressure or to recover refrigerant, there is always a risk of accidentally venting refrigerant. This is why low-loss fittings are necessary. Low-loss fittings work just like your standard garden hose nozzle. If you use a garden hose without a nozzle, you'll notice that a few drops of water still escape the hose after you turn off the supply. If you have a nozzle on the other end of the hose, you can control when the water stops flowing with more precision. This is akin to what low-loss fittings do when recovering refrigerant.
Low-loss fittings are only needed when recovering from appliances containing ODS and their
In this module, we
substitutes.
discuss the use of access fittings, piercing valves, and low-loss fittings in our recovery procedures. The EPA mandates the following. Access fittings must be leak tested before use. Solderless piercing valves cannot stay on equipment after servicing, and low-loss fittings must be used whenever connecting refrigerant hoses with CFCs, HCFCs, and their substitutes.
Okay, let's go to recovery quiz. Okay, this for type 1. Let's continue your attempt. Let's start. Okay, we have now 30 questions. Okay. A near azeotropic plant will contain one saturation pressure valve, one high saturation pressure valve, two saturation pressure valves that are closed, two saturation pressure valves that have big difference. For azeotropic, we have two saturation valves with a big difference. A zootropic plant will contain this one with big difference to saturation that are closed. Okay. Yeah, I don't remember this too much. Access fittings need to be leak tested before recovering refrigerant. Yeah, are used to gain access to close the system. Are used with all of this. Defrost heaters can be used to increase the temperature of the refrigerant. Can be used to increase the refrigerant recovery speed. Yeah. Yeah. Okay. If the compressor is not working, I don't know the correct answer for this one also. If the compressor is not working and we are performing a passive recovery, we need to take step to do what? Secure recovery machine, vacate the area, ventilate the working space, release trapped refrigerant from the compressed oil. If the compressor is not working, okay, and we are performing passive recovery, we need to secure recovery machine, ventilate the working space. Ventilate. Okay. If the pressure of the system found to be 0 psi, can we recover the refrigerant from the system? No, we can't. If the pressure reading and expected pressure are far apart, which of the following are possibly contained in the refrigerant? If the pressure reading and expected pressure are far apart, which of the following are possibly contained in the refrigerant? Non-condensable, water vapor, nitrogen. Nitrogen and water vapor also non-condensable, so all of above. Let's say we have a system with an operating compressor and the capillary tube is completely restricted. How many access valves do we need to recover the refrigerant from a system that is sealed? If we have system with operating compressor, okay, and the capillary tube is completely restricted. Capillary tube completely restricted. Access valve, we need only one access valve. Solderless piercing valve attend to leak over time, are for permanent use, should not be left. Both A and C. System dependent recovery is the same as passive recovery. Used to pressure of compressor, can be used for appliances. System dependent recovery until 15 pounds. We can use a known refrigerant PT chart to see if there are non-condensable in the refrigerant. Always true, only true if we can measure the refrigerant temperature. Only true if you can measure pressure and temperature. What the approximate pressure of a storage container of R22 that's stored at 75? Okay, we must open the PT chart. Okay, this is big problem. Okay, cancel. Can we open this in new tab? Now we have R22, okay, at 75. Okay, we need here R22. Okay, this R409, R11, R11. We need here R22. Okay, let's go down, go down. R22 is here, for which temperature is 75. R22 here, this line. Okay, and 75, this mean 132. This is the nearest is 131. What is the approximate pressure of storage container of R404 at 60? R404 at 60, 40, where is there? 402, 409, 404, yeah, here. Which temperature? It's 60 Fahrenheit. So for 404, let's go to 60 Fahrenheit, this line, 1, 2, 3. Okay, this line, yeah, so 1, 2, 3. 1, 2, 3, this means the nearest is 125. What should we do to recover refrigerant from a system with a compressor that is not working? Select all that apply, tapping the compressor with the biggest mallet to maximize surface area, tapping the compressor with a rubber mallet so we don't damage it, yeah. Heating it with match, heating with heating blanket, yeah. When performing active recovery and the compressor is working, we must recover to 90% of the fragrant charge. While it's working, it's 90. Not working, 80. While it's working, 90. Or 4-inch vacuum. Either A or B. Which method of monitoring fill level is the most accurate? The gross cylinder weight. Which methods are approved by EPA to monitor fill level of recovery cylinder? Mechanical internal flow devices, electronic shut off devices, gross cylinder weight. This all are approved. Which of the following are types of low loss fittings? Select solder type low loss fittings, manual, low loss, automatic, hybrids, manual and automatic. I think. Which of the following, I'm not sure of this one. Which of the following valves do we check if we suspect that the non-condensable are present? Okay, which is the values? Okay, refrigerant pressure, humidity, refrigerant type, refrigerant type. Non-condensable vapor, non-condensable is like water vapor or something, so we'll check humidity. You are servicing an appliance that contain R134A. Which of the following can use to recover the refrigerant? Recovery cylinder used HCFC, recovery cylinder used for HFC 134A. We need separate recovery cylinder for each class of refrigerant. Example HCFC. For example, we can't use the same cylinder to recover CFC and HCFC refrigerant, but we can use the same cylinder to recover different. No, we can't use the same cylinder to recover different refrigerant. An active recovery machine is required for all systems. Passive recovery is a thing that in past. An active recovery machine is required for all systems. No, passive recovery is not from the past. For both active recovery and passive recovery, We must recover 80% of the appliance charge if the compressor is not working. Yeah. If a refrigerant pressure reading are not stable, we can use its temperature reading to compare to its PT chart to check for non-condensable. We can use the temperature reading to compare its PT chart checks non-condensable. Yeah. Installing both high and low sides access valves will increase the recovery time. Yeah. Low loss fittings are only needed when recovering from appliances containing ODS and their appliances. No, we can use low loss anytime. Low loss fittings are required for service and appliances containing CFC, HCFC, and HFC because they are because of venting yeah, they protect us from venting. System dependent recovery capture refrigerant in pressurized container to keep it fresh. No, we we generally want to leak test access fittings after servicing to make sure it doesn't have leak for the next service. This is to save us time for leak testing access fittings the next time. Yeah, I'm not sure of this one. When the compressor is not working and we are performing a passive recovery, we need access to access the system for both high and low. Yeah, let's check it. Okay, we answered all the question. Mark it for questions. Let's submit. We have 8 of 10. Let's see the wrong answer. This is number 5. If the compressor is not working and we are performing a passive recovery, we need to take a step to do. Let's see the correct answer. If the compressor is not working, there is likely refrigerant trapped in the compressor. So release trapped refrigerant from the compressor oil. We need to take measure to release the trapped refrigerant so we can recover it appropriately under EPA section 608 regulation. Release trapped refrigerant from the compressor oil. Okay. Number 10, system dependent recovery. System dependent recovery all of correct is the same as passive recovery. Uses the pressure of the compressor, can be used for appliances with all of above. So system dependent recovery is for all. Number 19, which of the following values do we check if we suspect the non-condensable? We measure the refrigerant pressure to check if it's non-condensable air pressure. So we are check the refrigerant pressure. Okay. 24, if our refrigerant pressure reading are not stable, we can use the temperature reading to compare it to its PT chart to check for non-condensable. False. Okay. Installing both high and low sizes access valve will increase the recovery time. Those will decrease. Oh, sorry, will decrease. I didn't take care of this one. 29. We generally want to leak test access fittings after servicing. Okay, so it doesn't have leak to the no. Every time we must check it before starting the test. Yeah, I suspected this one. Okay. Okay. So here all is done. We passed also the test here. So in this video, we finish the recovery for type 1. We finish refrigerant properties, we finish refrigerant requirements and recovery requirements and recovery procedure and recovery equipment, and we finish the quiz. The next video we will finish this servicing, and if we have time we can finish also safety. So we finish this video and we'll continue at the next video.